Using a smaller, cheaper, serial-driven LCD screen with your Raspberry Pi can cause a lot of issues when it comes to frame rate in games. But with a different driver and a few tweaks, we can get to a really playable gaming system, even using some of the very cheap, generic LCD screens from China. So, let me show you how it's done. Hi and welcome to Bytes and Bits. If you've been using a Raspberry Pi with one of these little SPI based LCD screens, maybe you're putting together a little retro games console, then you'll have found that these produce a pretty atrocious frame rate, something like 5 frames per second, again because of this serial data channel which they use. In one of my previous videos, we had a look at setting that up using the standard software, and we could see that with a few tweaks and really just increasing that SPI data rate, we could get to a usable frame rate. I wouldn't say it was a great frame rate, but it was a usable frame rate. In this video, we're going to take that one step further. We're going to ditch the standard driver software and install a much better, better optimized as well set of driver software. And that will get us heading towards this sort of idealized 60 frames per second. So let's get straight in and see what we're going to do. In my previous video, where we used the standard drivers for these LCD screens, and I'll put a link up in the top right hand corner there. We worked out that to get our 50 frames per second, we would need to drive our serial bus at around about 150 megabits per second, and that just wasn't possible. We were really sort of topping out on my particular screen at around about 24 megabits per second. So that technique of simply spitting the information out on the serial channel faster obviously came to its limitations. So what we need to do is have a look if there are any other ways in which we can optimize how we send data to our display to actually create our animations. So the second way to get more frames per second coming out across our serial channel is to send less data per frame. So in this way, we reduce our data rate simply by sending less information. Now that doesn't sound like a very good idea, but if we look at our individual frames, so let's look at 4 frames in our Aladdin game that we were using, and then examine a particular block of pixels on each of these frames. If we look at each of these, although our animation in this particular game is full screen scrolling, this little block of pixels doesn't change at all, even over 4 frames. So in between frames, we'll actually find that there are quite large blocks of the actual screen that don't change. And the way these LCD screens work is that once we have set a pixel's color, it won't change unless we overwrite it. So if we only send across the pixels which have changed on each frame, all of a sudden we're no longer sending 2.5 megabits per frame, but perhaps maybe a quarter of that or a tenth of that, or maybe even less for some games. So all of a sudden, if we combine this with our faster SPI rate, we can jump from our sort of 15 to 20 frames per second on our previous optimization up towards our 60 frames per second, which is really what we need to achieve that super smooth animation. So we'll obviously need some software to make all of this happen. And luckily there's a very talented GitHub user who goes by the name of JUJ. And if you head across to his GitHub account, you'll find an FBCP ILI 9341 repository. So if we go to that, this repository then is designed to create exactly what we've been looking for. So this idea of both speeding up the SPI bus data rate, but also then doing this intelligent screen update where we just send pixels that need to be updated out to the screen rather than just blindly sending the entire pixel display every single frame. Now the code is slightly more complicated to set up and use, but we'll go through that step by step so you can see exactly how this all fits together and how we can get it working for your particular display. So if we look at the repository page and scroll down through the README section, there is an installation part that takes you through the whole process of getting this up and running. Now the driver is termed an ILI 9341 driver, and that's what it was originally written for, but it does cover a wide range of screens. So whatever small LCD or SPI LCD you're using, this driver is going to be able to work for that. So the process of installing it is that first of all we have to remove any of the previous driver software. So if you've been following through my previous video where we installed just the normal sort of WaveShare stuff, we do need to make sure that that's not in place anymore. So I'll take you through how to remove that. We then need to download the Git repository from this repo, build that. So there is a bit of terminal-based coding we need to do, or not so much coding, but typing in some commands. And we need to then select which options we need to build this software with. And you can see here there's a range of things that we can do depending on which particular LCD screen we're using, or which particular chips perhaps that uses, and so on. It does look a little bit complicated, but it's not so bad once you get down to the nitty-gritty of it. And as I say, that's what I'm going to take you through now to put together. And I'll do it through with my WaveShare one, and then I'll swap across to a different display, which is an ultra cheap little LCD TFT screen, and to show you that we can actually get any of those up and running as well very easily on our Raspberry Pi, even though they're just designed more for sort of the Arduino market. So I'm back onto my Raspberry Pi, and I'll need to be able to access the terminal on this. So I've connected up my HDMI display and a keyboard and mouse. If you're happy using SSH, then please use that. But we do need to have some way of accessing and viewing the Raspberry Pi without the LCD screen. And mine is set up where we were at the end of my previous video. So we're running Emulation Station or RetroPie, and it's all set up with the WaveShare drivers on my LCD screen, and that's all up and running and working okay. So we need to then start removing those existing LCD drivers. So I'm going to come out of Emulation Station, and we will need to edit our config.txt file. Okay, so we're going to do sudo nano /boot/config.txt. And this is the file that sort of sets up a number of the services inside our Raspberry Pi. So if I scroll down a bit on here, now if you haven't yet installed any LCD drivers, then obviously some of these bits will not be in place, so you won't have to remove them. But there's a couple of things we do need to make sure we do. So down here, we have the command line that turns on the hardware SPI channel. Now the new driver has its own version of this software, which is an optimized SPI driver. So we actually need to turn off the hardware driver through this config.txt file. If we don't do that, this will interfere with the operation of the new driver, and it just simply won't work. So we need to turn off our SPI driver. A bit further down here then, okay, so the audio, we can leave that, but this line here which invokes the WaveShare driver, or if you've got some other LCD driver, you'll find something similar there. We need to then obviously turn that off. So all I'm doing here is I'm just commenting out these lines, so they're just sitting in there if I ever need to reinstall them. But we need to turn off that driver so that we can then of course use the new one. Now, at the bottom of my code here, I have some HDMI display setup parameters. Now, if you have not yet installed an LCD driver, you might find that you don't have this block down here. It's not essential, but it is good to reduce the HDMI display resolution down so that we're not having to deal with the full HD screen each time. We know that our LCD screen is going to be a much lower resolution, so taking our HDMI resolution down just helps the process of translating that screen display into the right resolution for our LCD screen. So if you haven't yet got anything in there, do have a look at what I've put down here. Again, all of the code that I'm doing here, I will put that into my main website. So each of these videos that I do produce a page for each of them in my main Bytes and Bits website. So I'll put links for that down in the description so you can get across there and not have to read this off the screen. But that little block of code on the end there, just as I say, sets up the HDMI display, and we will be tweaking that a little bit later on to just gently improve the quality of our display. So that takes it out of our config.txt file. So if I do Control X to come out of this, and yes to save that and with the same file name. I also need to edit the boot up file for my Raspberry Pi. So I'm going to do another sudo nano. So this is in the etc folder, and it's the rc.local file. So if we go in there, if you have, again, installed one of these Waveshare drivers, you will probably see a line that looks like that, where it's FBCP and then ampersand. Again, if you haven't yet installed anything, this won't be here and you won't have to worry about it. But we need to remove that. So that is another frame buffer copy piece of software, which the Waveshare style drivers use. And of course, that's going to be replaced by our own one now with this ILI 9341 driver. So let's uncomment that, and then of course X to save that, Control X, sorry, and yes to save that, and so on. So that's removed the software from the boot up configuration on our Raspberry Pi. So obviously we'll now need to reboot so that that's all gone. So my Raspberry Pi has booted back up, and going through RetroPie, I've quit out of Emulation Station, so I'm now at the terminal prompt. So to begin with then, we're going to have to download this repository, and we actually have to compile and build the code ourselves with the various options that we need. So first of all, we need to make sure that we have the ability to create make files for the compilation. So we need to install a little utility called CMake, which is probably already on your Raspberry Pi. But just to make sure that it's there, we just do the sudo apt-get install CMake, and that makes sure that that little application is in place. We're then going to have to download the repository. So we're going to do that into our home directory. So if you're not already in your home directory, do your cd tilde, and that will take you to your home directory. We're going to use git to clone the repository down, and the repository we want to clone is in github.com/ and it's uj/fbcp and then ili9341.git. So that command there uses git, and that will copy that repository from the website down to our home directory. So we now need to, if I do an ls to see what's on the file now, you can see that I now have that FBCP ili9341 sitting in a folder. So I want to cd into that, so FBCP, so let me just change into that directory. And we now want to make our own version of the software with our particular settings for our LCD screen. So we're going to build that inside our own little folder. So we need to make a folder for this. And I'm going to call my folder build, because that's just the easiest way of doing it. We're then going to change inside that folder. Sorry. So we're now sitting inside that folder. And now we want to create what's known as a makefile. So makefile is a set of instructions for the C compiler, which will put together the software and compile it for us with certain sets of options. So we need to work out what those options are. So if we come back over to the GitHub repository for this project, you'll see that we're basically running through this set of instructions that are detailed out here. So we're currently about to use the CMake app to create the makefile for our particular setup. So we need to have a look at these options down here. And this is where it does get us slightly confusing as to which ones you need to use. So you can see that we have here various sets of sort of pre-made LCD screens. And it's a matter of working out which one you've got. And I find the easiest way to do this is to have a look at the resolutions of your screen, sizes of screen, and see if you can find one that sort of matches in best with yours. So we've been using the WaveShare drivers, and I've found that for my particular LCD screen, this WaveShare driver here, which does say for the WaveShare 35B, and I know if you looked at my previous video we were using it as a 35A, but this one quotes the correct resolution, and I know mine is compatible with WaveShare, so for me this one actually does work for my display. And this is where sometimes it's going to be a little bit of hit and miss. I will take you through this process of making the executable file for our particular LCD screen. But sometimes we will do that and it won't work. And what we'll need to do then is come back in here, delete what we had done before, recompile it with the next set of options, and then try that out. So that's where this bit is a bit more complicated. So we will have to build the software, test it out. If it doesn't work, rebuild the software with different options until we get a working set of software. So I'm going to go through one which I know is going to work on my screen, just so we can see what happens when you get it right. And then I'll show you how to rebuild that software as well. So I'm going to use this option here, which is the WaveShare 35B. I'm going to turn that on. And that will set up all the correct pins and the correct way in which the software is going to talk to my LCD screen. We then need to come down and say, we'll go through some of these options a bit later on. But we need to come down to setting the speed. So the first option then, as I say, sets up the connections and the way in which it's driven. And then we're going to come down here and then work out how fast we want to drive our SPI channel. So we can see here we have this clock divisor number, which must be an even number. Now what that does is the main chip inside our Raspberry Pi runs at around about, well, the clock inside that is running at around about 400 megahertz. So we need to then divide that down to get our SPI clock frequency. So that's all that's going to happen here. So whatever we set this divisor number to be, we will divide 400 megahertz by that, and that will give us our SPI clock frequency. So again, we need to make sure that that is our screen is capable of coping with that. So I'm going to start off with a higher divider value, just to make sure that when we do try this screen out, if we have got our screen specification wrong, then I will know that that's what's wrong, and not that we are driving the screen at too high a frequency. So I'm going to start off with a clock divisor of, as they suggest here, 30, which will take it down to about sort of 12 or 13 megahertz, which I know that my screen is capable of coping with. So then if I don't get it to work, I know that I've just got other settings wrong. Once I get a working screen, I can obviously then start playing around with this clock divisor to try and get myself to as fast a clock rate as my screen will cope with. So let's go and recompile or create our makefile and compile and see if we can get something working. So I've already typed out my CMake line. I do struggle typing and talking at the same time. So I'm using the CMake command. I have then set the option for that Waveshare 35B with the ILI 9486 driver chip. I've then set my DSPI bus clock divisor to 30. And then after that, I've put a 2 dots, which means that it will create this CMake file in the folder above the one we're currently in. So I'm currently in the build folder, so it will actually make this make file in the folder above that. So that's what the 2 dots are for, and that is actually important to put that in there. So let's run that command to get that make file created. Okay, so let's create those build files. And now we just need to make that. So we do make and -J. Oh, let's come out of my caps lock. And that should now have given us, so it said it's created a build target FBCP ILI 9341. So we should be able to just run that file. So sudo and FBCP ILI 9341, and that should hopefully run our LCD screen. And there we have our LCD screen up and running. So you can see that it is now mimicking my HDMI source. There is a little bit of data at the top of the screen, which is a little bit of statistics, which will show us how well the screen is running. And we can leave that on for now. It's on by default when you compile, and that just lets you see how well the screen's running. I'm going to leave that on for now, so as we go through, we can see that if we get better frame rates, just how better they are. And then eventually we will get to the final set of parameters which we'll build our executable file from, and at that point we can actually turn off the statistics, and that then won't get in the way of our final game display. But we now have a running piece of code. And that at the moment we have had to run that by hand by typing in that very last command. So we need to, of course, make sure that this runs when we first boot up our display, so that we can actually get it running inside our RetroPie. So Control-C gets me back to my command prompt, and then I need to reboot my Raspberry Pi. And there we have our RetroPie running on our LCD screen. So in the previous videos I had been using a Super Nintendo game, Aladdin, to test out the performance of this. So let's go into that game and see how that fares on this new setup. So the game has a sort of start screen where it goes through a couple of the levels, and we use that then to compare, because we have exactly the same sequence of animations. So as we look at the display, we can see that we're getting a reasonable frame rate, but now and again the display seems to turn very blurry. So if I pause the animation at this point, we can see that up in the top left corner we have a frames per second indicator. So at the moment we're hitting 20 frames per second. But what happens with this driver is that it does all of its optimizations, but if that's not enough to hit the target frame rate, it actually has a further optimization where it actually interlaces the screen. And what that means is that instead of sending every single row of pixels out to the screen, it actually only sends every other row of pixels for one frame, and then in the next frame it will send the second half of that image. And what that means really is that we end up, because the display leaves behind the older pixels, when we send the first half of the image on, say, the odd numbered pixel rows, we get one frame displayed then. The second time when we put in the even numbered rows, we're actually displaying a second frame. So we actually end up with half of one frame and half of the next frame on screen. And that adds to this sort of motion blur effect. So the number you see there, the 20 is the frames per second. The I and the P then is interlaced and progressive. Sometimes you'll have a mixture of two numbers where it's doing some interlaced frames, some progressive frames. And then the number in red after that, that's actually the number of frames that have been dropped. In other words, just frames that just did not have enough time to display at all. So really we're going to have to increase our optimization and increase our SPI speed to see if we can then get it working just a bit better. And this is what I mean about having to continually tweak this driver setup. So we're going to have to go back in, rebuild it with some new settings and see if we can get it to work that bit better. So I've quit out of the game and I'm now going to quit out of Emulation Station. And that takes me back then to my Raspberry Pi console. So we're going to have to recompile a new version of the software. So at the moment I'm in my home directory. And if I list that, you can see that I have that driver folder there. So I'm going to CD into that. So CD FB, and I'm in there. And now we have that listed out. There's a bit more than I thought there. But we know that we have a folder called build, which is where we actually built up that version of the software. So I'm going to completely delete that directory. So I'm going to do rm-r and then my build directory. And we get rid of that. I'm now going to redo the commands that we did before. So I'm going to make a directory called build. So I'm going to remake that directory. I'm going to cd into it. And then I'm going to remake my make files. So if I just use my up arrow, I can go past the last commands I used, and we should find, eventually, the one where we made the make. So which is that one there. So again, we're targeting our WaveShare because we know that WaveShare driver actually does work. It's just this clock divisor that we have to play about with. And this really is where we now have to start tweaking this. And this is really going to be trial and error on your particular LCD screen to find out which values let you run it as fast as possible while still keeping it working. So we've seen that 30 is a bit too slow and we end up having to do too much of that interlacing display. So let's take it down to 10 and see what happens there. So again, we're going to make that. And then we have to do our make -j to actually compile the files. So that creates a file with the same name as before. So if we reset our Raspberry Pi now, that should then boot up, but now using this new version. So let's go through and reboot then. So I've booted back up again. And as you can probably see, although my HDMI display is fine, so I know that the Raspberry Pi is up and running and that RetroPie is working. As you can see on the LCD screen, it's just we've lost the display now. So obviously setting that divisor to 10 is setting the SPI bandwidth just a bit too high for the screen to work. So it really is a matter now of just repeating this process until we find that nice sweet spot for it running fast enough to give us a good frame rate while still giving us a nice clear display. So after some playing around, simply going through that process of rebuilding it with different settings, I finally got to a divisor of 18 that is working for me. So remember, you must always use an even number. I found that 16 let me see maybe half of the screen at a time, so it was no good at all. And 18 has given me this display here, which is pretty stable so far. At that speed. So let's have a look and see what it's like with the actual game itself. So if we come in here and again start up that Aladdin game. So we're really looking here then at that frame rate and the sort of skip frames and so on. So if we look at that, we can see that we're actually getting a reasonable frame rate. And the interlacing is still happening now and again, but not as much. And definitely the skip frames is a lot less. In the actual gameplay then, for me, that looks pretty good. We're getting a nice frame rate, so we're sort of up in the 30s and 40s and so on consistently. The motion blur has pretty much gone. It's still there sometimes, but nowhere near as much as it was. So for me, I would rate this as now a very playable system. That seems fine. And if we compare it to the very original, so that's the default settings unoptimized using the normal sort of waveshare driver, we can see that it really is a very, very marked difference. Okay, it's not absolutely perfect. Yes, we still have a little bit of that interlacing going on, but I think we now have a very playable system. So there's a couple of extra things we need to do to finish this off. And the first is to remove those statistics on the screen. So I'm back into my console and I'm going to change directory into my FBCP. Again, I'm going to remove that build directory. I'm then going to make it again and change into it. And then going to find my last cmake command. Okay, so we did that, and I'm now going to add a new parameter in here. So it's -d statistics. So d statistics. There we go. Just make sure that's all spelled correctly. And that needs to be set equal to 0. The default setting for that is 1, which displays that sort of basic statistics. So I'm going to run that, reset the Raspberry Pi, and see what happens. And there we have a nice clean display now, ready for us to start gaming. So there's one very final optimization which you can do. It's not entirely necessary, but it does make a very slight difference. And that is to change the HDMI resolution so that it matches our LCD screen. So at the moment, this FBCP driver is taking, in effect, pictures of the HDMI display and then scaling that to fit on our LCD. So especially some sort of smaller text and so on can sometimes get a little bit corrupted doing that. So we can just simply come in here. So we need to change our config.txt file. So we need to do sudo nano, and that's in our boot directory, and it's config.txt. So this was one of the files we edited right at the very, very start of this video. And down the bottom we have our HDMI parameters. And we were setting up a custom little resolution there. So HDMI group 2 mode 7 lets us set up a specific resolution on our screen. So what we can do here is we can change that. So my particular screen is 480 pixels by 320, and we want to run that at 60 frames per second. So if I save that, the problem with doing this though is you must do this once you have everything else correct for your LCD screen and you're happy that your LCD screen is actually working correctly. Because once we do this, some of these LCD screens, if we set our HDMI to match that resolution, we will actually lose our HDMI signal. So you'll have, if you want to come back and edit this or make any changes, you'll then have to go through your LCD screen or else use SSH to remotely log into the Raspberry Pi. So as I say, this is something you don't have to do. It is probably worth doing, but as I say, only do it once you are sure that everything is working on your LCD screen. So I'm going to run this and we'll see if it makes much of a difference. So let's come out of this, and of course then we'll have to reboot the Raspberry Pi. So that's it running with the matching HDMI resolution. My HDMI monitor is still running actually, but there we have it on the LCD screen. And to be honest, I think yes, especially the text down the very bottom there, the very bottom menu, those thin lines, they do seem much clearer with this. If we actually go into then a game, so let's come back here and let's try that Aladdin game again, see how that works. You can see again the text ratio there has changed. And if we come into the actual display, not sure if it has made a difference there to the actual game display. But definitely that is doing as best as it can. So I'm sure that we will get certain improvements in certain places. But I say, it's because it's such an easy thing to do at the end, I think it's probably worth doing. But as I say, it's not made any change then to the quality of the graphics and the frame rates and so on. But anyway, that's something that you can do if you want to. But say, do make sure you do that after you've got the LCD screen working. So using this JUJ driver then, you should be able to get a pretty good gaming display on any of these relatively cheap SPI based LCD screens on your Raspberry Pi. Now even the one I'm using here, which is specifically designed for the Raspberry Pi and plugs into the GPIO port, those are around about what I was paying, around about £25 for that. The sort of HDMI based ones tend to come in at around about the 40, but there are a set of little LCD displays you can pick up for around about £10, which tend to be based around another little sort of ILI 9341 display driver. And a lot of those are aimed at the Arduino market. They don't come with a Raspberry Pi connector, but of course they are quite cheap. This driver that we've just been using can of course be used to drive those pretty much as well as we've been driving this Waveshare style one, and in actual fact that the Waveshare one I'm doing is actually running quite slowly. So I haven't had time to cover that in this video. I think we've already hit about sort of 40 minutes almost. But the actual techniques are the same, but I'll actually go through the connecting that up and then setting up some of the parameters, some of the extra parameters when we compile our driver software. We need to put a number of extra parameters in there which allow us to specify which pins we're using to drive one of these generic displays. But I'll put that into a separate video. But I say, if you have got one of the Raspberry Pi based ones, then obviously this driver will give you much better performance than the standard drivers that come with them. So there's been quite a lot of code and things to remember and type in out of this video. So please do make sure you visit my main website where each of these videos that I produce, I put in a page which will help you with all of the code and things you need to remember for that particular project. So if you look in the description down below, you'll find a link to that web page, and you'll get all of the codes that you need to type in for these parameters and so on, and links to all of the repositories and everything you need. So if you have enjoyed this video and you want to get more videos like this, do please click the subscribe button and click on that notification bell to make sure that you get a message every time I put up some new content. And as I say, if you want to have a look at those really cheap LCD screens for around about £10 for a nice 3.2 inch display, then I will cover that in one of the next videos using this driver, but showing you which of the parameters you need to set up for that. So hope you're having fun with all this. Have fun with your LCD screens and playing your retro games. Have a go at building a little handheld or something, and I will see you in one of the next videos. Bye for now. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.